All right. So in this lecture and the several following, we're going to talk about catalysis. So catalysis is a field that is near and dear to my heart. This is where I do my research. Catalysts are involved in just about everything that you touch. Has seen a catalyst at some point along its production. There's an estimate that 35% of the world's GDP depends on catalysis. So, catalysts are important to chemical engineers. They help chemical reactions proceed more efficiently. And because of that, we need to know how to incorporate them into reaction. We need to not only know how to incorporate them into reactor design, but we also need to know a little bit about how they function. And probably when you go to take senior design next semester, you'll probably end up researching reactions that are promoted by catalysts and identifying the types of catalysts that are most effective for the particular reaction that you're looking at. So it's good to have some working knowledge of how catalysts function. So first, let's define catalyst. So a catalyst is a reactive intermediate that promotes the production of a large number of product molecules. So a catalyst is a reactive intermediate that promotes production of a large number of product molecules. So if you hear of something being catalytic, what that means is that thing is promoting the production of a large number of products. And catalysts can take on various forms. Sometimes catalysts, you may think of a catalyst as being, for example, some sort of a radical species that is promoting the production of gas phase molecules in a heterogeneous catalyst is less reactive, so it's more stable, but still is able to promote turnover more rapidly, or promote rapid turnover of reactants into products. So another way to think about catalysts is that they provide lower energy routes from reactants to products without being consumed. And so we'll demonstrate this a couple of times throughout the lecture. So one example of a catalyst is that chlorine catalyzes the decomposition of ozone. So in the absence of chlorine, ozone reacts with oxygen atoms, and this is an atmospheric reaction, so maybe we don't expect atomic oxygen to be present in the gas phase closer to Earth, but further up in the atmosphere, atomic oxygen can exist. It reacts with ozone to form molecular oxygen. And the activation energy for that reaction is 20 kilojoules per mole. Chlorine acts as a catalyst in the conversion of ozone to oxygen. So what it does, so chlorine plus ozone goes to O2 plus a chlorine oxygen complex, and this has an activation energy of 1 kilojoule per mole. And then the chlorine oxygen complex reacts with another oxygen atom to form O2 and Cl. This has an activation energy of 2 kilojoules per mole. So you see, both of these reactions have dramatically lower activation barriers than the original case. So 1 and 2 kilojoules per mole, much lower than this 20 kilojoules per mole. That's the effect of the chlorine catalyst that's providing a lower energy route from reactants to products. And it's also without being consumed. So the chlorine participates in the reaction mechanism, but is ultimately fully regenerated. So if I take a net reaction here, so the net reaction That is the same as in the non-catalytic case. But we've gotten there. So we've gotten there by going over energy barriers that are a lot smaller. So it's the same reaction, but the kinetic pathway is more favorable. So we could create or sketch an energy diagram for this process. So that's supposed to be a straight line. So let's see if I can make that a little straighter. And not quite. Just that's supposed to be straight. It's not supposed to curve here. So we'll say energy, and this is arbitrary units. And down here we'll say reaction coordinate. So in the absence of chlorine, we have something that looks like this. And when we have chlorine present, then we have something that looks like this. And this drawing is not to scale. It's just for illustrative purposes. We'll say this is all energies are relative. We'll say this is the 0 line. But basically what you see here, the catalyst, the chlorine catalyst, is providing a lower energy route from reactants to products. So if you imagine that this is a landscape, or there's 2 landscapes here that you have to walk across to get from reactants to products, it's energetically more challenging to walk over this large hill than it is to walk over these 2 smaller hills. So the catalyst is providing this lower energy route. And in fact, for the ozone species, or the collisions need to have less energy in order to transverse these barriers than they do to transverse this one. Hence, this pathway is more likely and is going to happen more rapidly. You'll notice that the catalyst is changing the kinetic pathway. It's changing the route from reactants to products, but it's not changing the thermodynamics. So the reaction energy, or the heat of reaction, that's a state function. So it doesn't matter how we get from reactants to products, that energy is the same regardless. So the catalyst is providing a lower energy pathway from reactants to products. But it alters the kinetics, not the thermodynamics. So the reaction energy, or the heat of reaction, remains the same regardless that we've used a catalyst. Okay, so let's look at a heterogeneous catalysis example. So again, let's draw an energy diagram. So this is energy over here, arbitrary units. And this axis is going to be my reaction coordinate. The reaction that we're going to look at is carbon monoxide oxidation. So in the gas phase, if this reaction were to happen, is that this oxygen molecule, the bond must break. So, and then the oxygen atoms must each find a carbon monoxide and bind to that. So we know that this oxygen molecule, there's a lot of energy in that oxygen-oxygen bond. So a lot of energy would have to be input into the system in order to get the oxygen-oxygen bond to break. So if you think about an oxygen molecule, 2 oxygen atoms, basically we'd have to heat that thing up such that the oxygen bond vibrates very, very strongly, and those oxygen atoms, they're vibrating so strongly that if they they happen to collide with a carbon monoxide molecule. That bond breaks and CO2 then forms. So the very minimum amount of energy that would need to be put in there is the amount of energy to get that oxygen-oxygen bond to break. And we know what that is. We can look that up on the NIST website. It's the energy of formation, or the heat of formation, of oxygen atoms in the gas phase, which is equal to 250 kilojoules per mole of oxygen. So if we wanted to draw out the kinetic pathway for this reaction in gas phase, we're going to draw so this here, it's actually 249 mole of oxygen, atomic oxygen. And so up here, we would have CO gas plus O gas. Down here, we have CO2 gas. And here we have our reactants. We have CO gas. In fact, let me draw that here. CO gas plus 1/2 O2 gas. And here we're talking about moles. So we have half a mole of O2 gas. So that's what that means. And the reaction energy for this is pretty exothermic. So it's pretty favorable to form CO2. But to get there, we have to cross this very large energy barrier. Now, if we carry this reaction out over a platinum catalyst, the energy pathway becomes much better. So we'll say compare homogeneous gas phase reaction with heterogeneous reaction using a platinum catalyst. So carbon monoxide and oxygen will both bind favorably to that platinum catalyst. The oxygen molecule will favorably break on that platinum catalyst, and the energy pathway is far more favorable than the gas phase pathway. So the first step in that, we would have carbon monoxide and oxygen bind to the catalyst, and they do this favorably. So I'm labeling this as CO star and O star, where the stars mean sites on the catalyst surface. So you can think of this as a platinum catalyst. Maybe it's platinum atoms on the surface, and those platinum atoms are hungry for species like CO and O, so they will bind them readily, which is why the energy goes down. The starred species mean that those species are bonded or adsorbed to the catalyst. So CO star is analogous to saying CO bonded to platinum. So we could also say same as writing C So now we have adsorbed these two species to the catalyst, so now they will combine. And when they combine, there is an activation energy. So I'm going to label this using the dagger symbol. The dagger symbol is often used to denote transition states, and the transition state is this location right here on the energy diagram. What's happening here, the oxygen on the surface and the carbon monoxide are combining. So they combine, and this is not drawn to scale, but basically they're going to combine to form adsorbed CO2. Adsorbed CO2 from an energy perspective is just slightly favorable, slightly more favorable than CO2 gas. And then the CO2 will desorb to form the CO2 gas. So the energy profile here, the pathway, the kinetic pathway, is much easier than the gas phase pathway. So this reaction is much more rapid on a catalyst than it is in gas phase. The bottom line for this is that molecular oxygen doesn't dissociate in the gas phase, but it readily absorbs to the catalyst and dissociates on the catalyst. The catalyst thus provides a lower energy route from reactants to products. And again, just like in the last case, the catalyst influences the kinetics, but not the thermodynamics. So that's kind of an introduction to what catalysts do. So let's now talk about types of catalysts. There's two broad classes. Those are homogeneous catalysts and heterogeneous catalysts. To be classified as homogeneous or heterogeneous, it depends on the phase of the catalyst relative to the reaction environment. So a homogeneous catalyst is in the same phase as the reactants. Let's say the reaction environment. So several examples of those. One is an acid catalyst. So protons bind to a reactant and alter the reactant's electronic structure, which then promotes the reaction. So an example of this is Fischer esterification. So what's going on there? I have an acid species and I react that with an alcohol in the presence of an acid catalyst to form an ester and water. So how the catalyst participates in this? So we take our reactant species. We've got lone pairs on this oxygen atom. Those are going to react with the catalyst. So they're going to modify its electronic structure. This then prepares the species to react with the alcohol. Which then promotes the reaction. And then regenerates the catalyst. So the acid is not consumed or generated within the reaction. What it does is binds to the reactant species, alters its electronic structure. The altering of the electronic structure allows reaction with the methanol. Once the methanol binds with the structure, the current structure is thus unstable, so this enables the relinquishing of the acid to regenerate the catalyst and form the products. Another example is an organometallic catalyst. For example, a ligated metal cation. So one example is a metallocene. So we'll say EG, which means, for example, a metallocene. So that might look something like this. Where I'm going to give the generic symbol M to stands for metal cation. So the metallocene is a metal cation that's bonded to two cyclic hydrocarbons. Another example is a rhodium complex. So in that case, we'd have a rhodium cation, and it's going to be bonded to different ligands. So these are examples of organometallic catalysts. An example of reactions carried out by organometallic catalysts are the Cauchy-Arlman mechanism for forming carbon-carbon bonds. So for example, if we have a ligated metal cation, so we'll again take our divalent metal cation, and we'll say that this is, the ligands are supported on some structure. And often the metal forms a hydride structure. So what this will do is form carbon-carbon bonds for alkene complexes. So the first thing that happens there is the alkene adsorbs to this metal cation. And actually I'm going to get rid of the 2 plus because it's just going to get hard to keep track of in drawing this. Basically, I have this ethylene here is adsorbing, forming a bond with the metal complex. The ethylene thus reacts with the hydride, form an ethyl. Another ethylene molecule then adsorbs. These two species now combine to form a C2 or a C4H9, so butyl species. The butyl species then cleaves one carbon-hydrogen bond to form a butene. The butene then desorbs, so we'll say minus C4H8, and this regenerates the catalyst. So what's happening here on this metal hydride, there's two places where species can adsorb. So a species can adsorb in this slot or this slot. The hydride by itself, this has one open slot. So that's what gets species to adsorb to the catalyst. And then once in these slots, if it's favorable, species will react. On the other hand, if the catalyst has a species adsorbed in one slot and there's an open slot and it would be favorable to cleave a bond, the catalyst will do that. So when we have these slots, they're called sites on the catalyst when one of those is open, as is in the case of the metal hydride or this ethyl species or this butyl species. Those are called open sites. So the open sites on the metal cation bind species and promote the reaction. Open sites are the places where ligands could bind on the metal coordination environment, but where no ligands are presently bound. So to get a good picture of what ligand or coordinated, what ligated metal complexes look like, the Wikipedia page actually has a pretty good picture. So I encourage you to look at that if that would be helpful. So another class of catalysts, homogeneous catalysts, enzyme catalysts. So enzyme catalysts are nature's catalysts. So every living being is comprised of enzymes. Enzymes are comprised of proteins. And sometimes they have metal cations. For example, hemoglobin has iron cation on it. So for example, one type of enzyme catalyst is an amino acid, where the amino acid acts as the catalyst. So enzymes are typically tailored to specific reactions. They're usually highly active for those reactions. A lot of times they work on one type of molecule or bond. So they'll bind with one type of molecule and they'll convert it. They'll bond with other types of molecules too, but they won't necessarily convert them. If the enzyme is tailored to the particular reaction, then the rate is enormous compared to that of the uncatalyzed reaction, being 1,000 times faster to up to 10 to the 17th times faster. So enzymes, they're very specific, but when they work for a particular reaction, they work really, really well. So how do they work? So this, I'm going to have to draw this, but basically I have an enzyme. So let's say my enzyme looks something like this. And I'll explain this in just a moment. So I have amino acids along this, and I'm just going to label these. So I have A, B, C. A, B, and C are sites where I have amino acids. And then all of this back here, this is some solid complex, protein complex. So this is my enzyme. So I react this with a reactant molecule. So maybe the reactant molecule looks something like this. we're going to call it a substrate. Which is just a reactant molecule. So the substrate is going to bind on this enzyme. So let's see if I can draw this here. This is supposed to be approximately the same drawing. I'm very bad at drawing. And so the amino acid groups then interact with that. So I have what the enzyme is going to do is it's going to bend and vibrate and move, and so that the amino acid groups are going to interact with this substrate. And so then again out here, this is this big solid thing. So it's a protein structure. So just draw this out here to kind of acknowledge that. So when the substrate binds to the enzyme, thermal fluctuations in the enzyme structure bring the functional groups into proximity with the substrate. What happens then is the reaction is carried out. So these functional groups help to promote the reaction. So we'll say reaction occurs. After that, the structure, so it's kind of got this substrate trapped in here. Once the reaction happens, though, the amino acid groups are no longer attracted to this molecule any longer. So they work on the substrate. They don't work on the product molecule. So once the reaction happens, they come back open. So this opens back up. So we'll say the reaction occurs. The structure, so the enzyme structure, opens back up and releases the product molecule. So the key here is that the substrate needs to be able to fit inside this cavity. Once it's there, it needs to cause the thermal fluctuations that cause the functional groups to come into proximity with it. Once those functional groups come into proximity, they need to promote the reaction. Once the reaction happens, the functional groups need to become unattracted to the molecule and cause the structure to reopen up. So the thermal fluctuations are going to cause reopening of that structure. And when they do that, the product will be released. So as you can see, that's a very specific process. So that's why the activity is often catered to just one substrate. Maybe other substrates can bind there, but not all of the processes happen that cause it to react. So maybe another species can bind, but it doesn't react, or it doesn't cause the protein structure to put the amino acids into proximity. Maybe it does, but maybe it gets trapped there. Maybe they don't leave. So really, enzymes are very, very effective, but only when they're operating on the types of substrates that they are designed for. When so the reaction is happening according to the conformational changes. So when this happens, we have a conformational change. There are many types of protein substrate reactions, such as salt bridges, hydrogen bonding network, van der Waals interactions, etc. Okay, so that's examples on homogeneous catalysts. Now I want to talk about heterogeneous catalysts. So a heterogeneous catalyst is in a different phase than the reaction environment. So often the catalyst is a solid, like not a dissolved solid, but a solid. And the reaction environment can be either a liquid or a gas. So some examples are supported metal catalysts. For example, a common one is platinum supported on alumina. So this platinum would be considered to be the catalyst, and the alumina would be considered to be the support. What reason do you think that we would have a support? What's the purpose of having this alumina? So the reason to have the support is to increase the surface area and also to spread the platinum atoms out. So platinum is very expensive. So if I have just a chunk of platinum, there's a lot of platinum atoms. If you imagine that chunk of platinum is some common shape, so think of it as being a sphere, cube. All of the atoms that are on the surface are accessible for catalysis. Anything that's not on the surface is inaccessible. Those atoms are thus wasted because they can't promote catalysis. Platinum is, of course, very expensive, so we want to utilize as much of the atoms as we can. So what we do is we bond platinum to a support that then maybe we can coat the support with platinum atoms that prevents the balling up of the platinum atoms. Platinum doesn't like to be in atomic form. It likes to bind to other stuff, right? So in the absence of other stuff to bind with, it's going to bind to itself. That's going to cause a lot of the atoms to get hidden. But if we can spread it out on a support, then we get better atom efficiency. So we use the support in order to increase the surface area or the atom efficiency of the platinum catalyst. So the way that this might look, so what we actually do is, in addition to this support, we would also have some sort of a high surface area pellet. And we first coat the pellet with the supporting material, and then we would add the catalyst to the support. So in this class, we often think of pellets as being spheres. So we have catalyst pellet. And this pellet is porous. So if I'm drawing here a pore network. So the pores creates the surface area. So there's many pores. It's a highly porous thing. The analog would be if you think about a sponge. So a sponge is porous, right? So there's a lot more surface area along these pores than there are on the surface of the sphere. So the pores is what's giving this thing the surface area. So surface area, in fact, let's say the area of the pore surface, we'll say the pore walls, is often greater than 100 meters squared per gram. So we're really increasing the surface area. So we'll coat these pores with the support, and then we'll add the platinum. So if this is, a pore, so this is our pore walls. So you can imagine a molecule could be traveling through this. We'll have little regions of support. And then on top of that, we'll get little platinum particles. And we'll have that all throughout the catalyst pellet. Another very common example of a heterogeneous catalyst is a zeolite, which is an aluminosilicate. So the zeolite is going to be an aluminosilicate material, and it's going to be porous. So if you think about the base material, just think about a silicate. So there's silicons and oxygens. So silicon ions and oxygen ions. The alumino means that some of those silicons get replaced with aluminums. Since aluminum and silicon have different charges, so silicon takes a charge of +4, whereas alumina takes a charge of +3, that makes a charge imbalance. This means that you get you can accumulate ions within the zeolite structure, which allows for the potential for acid catalysis. So because of that, zeolites are commonly used as catalysts. One of the industries where they are widely used is the petrochemical industry. So they can accommodate ions such as copper, hydrogen, which can act as catalysts. The mismatch in the formal charges in the crystal structure between this, for example, this alumina silicon, creates both Lewis and Bronsted acid sites. So we'll say mismatch of formal charges. And those can act as catalysts. So when we talk about Lewis and Bronsted acid sites, the Lewis, that means it's an electron acceptor. The Bronsted is a proton donor. So much like in the homogeneous case example, this allows the altering of the electronic structure, which causes the reaction to happen. So an interesting example here is a recent collaboration by Bill Schneider and Raj Gunder, which was published in the magazine Science in 2017, where they're looking at the selective reduction of NOx. In a copper exchanged zeolite. So basically, what happens, the zeolite is this porous structure. So if I draw probably poorly because I am very bad at drawing, this isn't going as bad as I thought it could have gone. Oh, there we go. Okay, so, all right, so this is, a porous structure. In this case, so there's copper ions, and they kind of loosely anchor at the surface. So what's going on in this particular reaction, NOx selective reduction, the NOx is going to, NOx is NO and NO2. Those species are going to react with oxygen and ammonia to form nitrogen and water. So what happens here, we have copper ions within this porous structure. So we'll say two copper ions come together. They're going to be bound to the ammonia. So the ammonia will bind to these copper ions. And now we need to react with oxygen. So what happens there? the oxygen promotes binding of these two species in order to, and they bond together via this oxygen atom. The oxygen atom thus breaks, forming a complex. And this is a key step in the mechanism. So the reaction then proceeds by coupling of dynamic copper ammonia species. So a key role that these copper species play is to, again, break this oxygen-oxygen bond. So that is all I want to say in this introductory lecture. Basically, to define what a catalyst is, show how they work, and give examples of both homogeneous and heterogeneous catalysts. In the next couple of lectures, we'll start to focus more on the heterogeneous catalyst and, for example, look at how heterogeneous catalysts are used in reactors, as well as derive mechanisms for heterogeneously catalyzed reactions.